Thanks, Eric. And let me first start by thanking the organizers of this great workshop for putting this together and bringing so many interesting people together. I will talk today about extensions of general relativity with limited curvature. And let me start with a short introduction. General relativity is a classical theory of gravity, and we know that it's going to break down as we approach very small length scales due to quantum effects. In other words, the theory is non-renormalizable. And there are many theories of quantum gravity that suggest that there might be some notion of fundamental minimal length scale below which there might not even be a notion of continuum spacetime. Space-time might be discrete at that scale, and the continuum might only emerge on very large scales, much larger than this fundamental length scale. As a couple examples, in sort of well-known theories of quantum gravity, there's some notion of fundamental length scale, such as the string length in string theory related to the string coupling to power that depends on the number of space-time dimensions, which is then proportional to the Planck length. And in loop quantum gravity, there's a notion of a minimal area proportional to the Planck length squared through a parameter called the Barbero-Imerzi parameter. And in all these cases, and as expected, this fundamental length scale might be of the order of the Planck length, or perhaps a little larger than this scale. And that's the scale where we expect to start seeing large quantum effects. Now, it's very important to try and construct top-down theories of quantum gravity, and there are many more examples that I won't really discuss, but let me highlight some of the things we heard in this workshop, such as causal dynamical triangulation, causal sets, and so on. But that's certainly a very hard problem. And therefore, I believe there's some merit in trying to do something alternative, which is to try to come up with a bottom-up description of quantum gravity, which would give us some notion of a low-energy approximation to what the full theory might be. And so we say that it's only then an effective theory of quantum gravity that will nevertheless capture some of the fundamental principles that the full theory might have, such as a notion of minimal length scale. So for instance, we could try to construct a nevertheless smooth theory of gravity, which would slightly modify general relativity, but which would have a built-in minimal length scale. Let me say that this procedure of trying to construct a theory from the bottom up is very common in the fields of particle physics, or more and more in cosmology, where the idea is that you want to impose some principle that you believe is fundamental, and then you try to constrain the unknown from the bottom up. And so for the rest of this fairly short talk, I'm just going to give you an overview of how we might do this in gravity and present some of the results. So let me start by showing how we can go on and build and bound limit some fundamental, how to bound some physical quantities, that's what I mean. So as a warm-up, we're going to start by looking at special relativity. So let us say that we start with just a non-relativistic free particle of mass m and a speed v, which at this point can be really unbounded. The Lagrangian is just the kinetic energy. It's 1/2 the mass times the speed squared. Now, to make this relativistic, we should bound the speed, and it should be at most the speed of light, which we take to be 1. And a way to do this is to introduce a Lagrange multiplier term in the Lagrangian of the following form. So chi is a Lagrange multiplier and multiplies the speed squared, and we introduce a potential for this field. Now we get a constraint equation by varying the Lagrangian with respect to the Lagrange multiplier chi. And the constraint is that the speed squared is given by the derivative of the potential with respect to chi. And if we choose this potential cleverly, then we find this expression, which tells us that the speed is always going to be bounded by unity for all values of chi. And so in that way, we we found a way to constrain the speed to be at most the speed of light. Chi here, we can think of it as being an auxiliary scalar field, or if you will, a non-dynamical scalar field. And if we solve this, well, upon solving this constraint equation, if we invert it and solve it for chi as a function of v squared, we can then substitute this back into the Lagrangian, and we're going to have an expression that only depends on the speed. And the result we get is precisely the Lagrangian that we know in special relativity. So it's quite neat that through this procedure, we managed to find what we expected. Now we can then start thinking about applying the same strategy to gravity. And this original idea dates back to the 1980s. And so sort of the same procedure would go as follows. We start with the action of general relativity, in this case, the Einstein-Hilbert term, which is the Ricci scalar, the trace of the Ricci tensor with respect to the metric G. And then to this action, we add a set of Lagrange multiplier terms. We're going to call these chi, that multiplies some curvature invariant functions I, which, as the name says, are functions of the curvature, the Riemann tensor, contractions with the metric, and possibly covariant derivatives as well. And then we have a potential for all of the auxiliary fields. Then we get a set of constraint equations upon varying the action with respect to the auxiliary fields chi, and they tell us that the curvature invariant functions I are going to be constrained by the partial derivatives of the potential with respect to these fields chi. And as expected, if we can find potentials that are that have bounded derivatives, then we're going to find curvature invariants that are also going to be bounded that way. As an example of how this can work out, let's consider two Lagrange multiplier terms. And so the curvature invariants we're going to look at are going to be constructed with the Ricci scalar and the Gauss-Bonnet invariant, which is a combination of the Ricci scalar, the contraction of the Ricci tensor with itself, and the contraction of the Riemann tensor with itself. And a motivation for this choice of curvature invariant functions is that when you look at them on a flat cosmological background with this metric, where a of t is the scale factor, they reduce to what is known as the Hubble parameter squared, which the Hubble parameter is the time derivative of the log of the scale factor, and the time derivative of the Hubble parameter, so the second derivative of the log of the scale factor. So if we can now bound these two curvature invariants, I1 and I2, we have solutions that are going to have bounded first and second derivatives of the metric, and therefore we can find solutions which are going to be non-singular in at least at the level up to the second derivative. And in fact, in the work of the early work of Mukhanov and Brandenberger in the 90s showed that you can come up with examples where the solutions are really non-singular, that are smoothly non-singular, and asymptotically they approached either the Sitter spacetime or Minkowski spacetime in their constructions. Let me say that, moreover, the background and the linear perturbations in these cases are at most second order equations of motion, which is always a desirable feature in physics. However, there's a problem with such a construction, and it's the fact that the theory can actually be rewritten if you solve the constraint equations and re-express the curvature invariants that are functions of R and the Gauss-Bonnet term into the original action. You can rewrite the full action as just a function of R and Gauss-Bonnet. And this is a type of theory of gravity that has been studied, and it's well known that it is problematic. In fact, we confirmed this, and we found that there's always some corner of phase space that's going to be unstable. And by that we mean there's either a ghost or a gradient instability. And for a discussion of what those are, I invite you to listen to the seminar I gave earlier this summer at Fields. Additionally, if you deviate from a background that is exactly FRW, so exactly isotropic, then as soon as you have the slightest anisotropy, it was found that you always have a ghost that appears. And that means the theory is always going to be unstable and therefore pathological. Yet, introducing higher space-time curvature terms in the gravitational effective action is quite ubiquitous, especially as you try to go to higher curvature scales. And people can indeed constrain such terms from the perspective of an effective field theory. But in the end, either your theories nevertheless remain singular in the sense that it doesn't achieve the feature that it has some built-in limiting scale, or it will, but then it's still going to be unstable, so the theory won't be well defined. So this approach is challenging. However, we came up with an alternative approach to the same idea that works a lot better. That's what I'm going to present now. So the setup is to first do a 3+1 decomposition of our spacetime. And so this is the idea is that we want to separate our spacetime into space-like hypersurfaces that evolve through time. And we define this through a time-like unit vector n. So time-like, so its contraction with itself is negative, and we normalize it to unity, so we take it to be -1. As I said, it's normal to the hypersurface sigma, and it defines an induced spatial metric on this hypersurface gamma through this relation where G is the full spacetime metric. Then we can further re-express the full spacetime metric in terms of a lapse function, the induced spatial metric, as well as a shift vector by projecting the time vector perpendicular to, if you first project it along the normal vector, that's the proportionality factor is the lapse. If you project it along the hypersurface, then you get the shift vector. Then with the normal vector, you can also define your extrinsic curvature on the hypersurface, as well as the trace of this quantity, which tells you about the mean curvature, and that's just the divergence of the normal vector. And the reason why we do this is that with these quantities now, we can fully rewrite all of the space-time curvature tensors and quantities, such as the Riemann tensor and so on, in terms of just spatial quantities such as the extrinsic curvature, the three-dimensional Ricci scalar, and so on. So now with this setup, we can apply the same idea as before, but rather than trying to bound full space-time curvature invariance, what we're going to do is to try to bound only spatial curvature invariance. So we're going to keep our time to be just some smooth variable, but then we're going to try to constrain our spatial curvature. And with the same strategy as before, we start with just the action for general relativity, and then we add a set of Lagrange multipliers chi, and multiply some curvature invariance functions. But now those are functions of just the extrinsic curvature, the induced metric on the spatial hypersurface, and spatial covariant derivatives. As before, we have a potential for all of these fields. Now, at this point, we really have to define what is our hypersurface. And the way to do this is to introduce another field. And there's a couple ways of doing it, either with a scalar phi or with a vector a. And if we have a scalar, then we can just take the gradient of the field. And if this is time-like, then it can be how we define our hypersurface. Or if we, again, just have a vector, which itself is time-like, then we can also use this to define our hypersurface. Let me say that this is very common if Lorentz invariance is broken, either fundamentally or in a spontaneous sense, as it is in cosmology when we have when we have fields like this, or if you just think of having a natural notion of a time direction. Yeah. So from here on, I'm just going to take a vector field rather than a scalar field. There's a slight difference between the two approaches, but they're very similar nevertheless. Then we have to enforce the normalization that the contraction of A with itself is -1. And we're going to do this with yet another term in our Lagrangian, in our action, with a Lagrange multiplier lambda that's going to make sure that we have the desired normalization. Now let me show a simple realization of this idea. So perhaps the simplest curvature invariant that we can first study would be just a trace of the extrinsic curvature, the mean curvature K. And with a vector field, then this is just the divergence of A. Then we write our action. We have at first the general relativity term. So this was, previously this was the Ricci, the 4-dimensional Ricci scalar, but when you do this 3+1 decomposition of the metric, it becomes a combination of the extrinsic curvature contracted with itself, the mean curvature squared, and the 3-dimensional Ricci scalar. Then we have the term that makes sure, then that ensures that we have the vector field A being time-like and normalized, so that it defines our hypersurface sigma. And then we have the terms that are going to limit our curvature. So chi is the auxiliary field, K is the mean curvature, and we have a potential. Now we vary the action with respect to the chi field, and from this we get a constraint equation that tells us that the mean curvature is constrained by the derivative of the potential with respect to chi. And if this derivative is bounded, then it's going to ensure that our mean curvature is also bounded. Now this type of constraint equation actually has a name, and it's the Coscoton constraint. And the reason is that, well, indeed we can show that this theory is exactly equivalent to a theory of the same name, Coscoton theory, which was developed by Abshorty, Chung, and one of the organizers of this workshop. And I talked about this theory a little bit at, again, during the seminar I gave earlier this summer here. And to see the equivalence, we can do a few manipulations. First, if we get the equation of motion for the vector field A and substitute this back in the action and perform a few manipulations, as I said, ultimately the action is equivalent to that of general relativity, and then an action for the field chi, which is the square root of the usual kinetic term for a scalar field, and a potential. And this theory has very interesting properties. For example, on a cosmological background, where the mean curvature is just 3 times the Hubble parameter, we can get solutions where the mean curvature is bounded. Therefore, the Hubble parameter will also be bounded, and solutions then look like non-singular bouncing universes. And furthermore, further studies showed that linear inhomogeneities about this background are always stable. Yes?
So I got confused. Previously you eliminated phi, but now it's still there. So
okay, so I'll come back. You can eliminate chi and rewrite the action without chi, but just in terms of k, or you can rewrite it just in terms of chi. There are 2 formulations of the same theory. It's just different manipulations you do to rewrite your action.
Right, but in this formulation, when you write the action, am I now going to vary chi or no?
Yes, and whichever way you vary your action, the equations are going to be consistent. Yeah. Okay, now let me discuss the relation to other theories, and here we're going to see another way of reformulating the theory. So one thing we can do is to, when you solve for the constraint, the mean curvature being the derivative the potential with respect to chi, if you can invert the solution for chi as a function of k, and you can do this whenever the second derivative is non-vanishing, then thanks to the Legendre transform, you can rewrite the previous action in the following form. So this term, k times chi minus the potential, that was just what we had to the right here. And so ultimately what we have, when the constraints are satisfied, the theory becomes equivalent to, again, we just have, this is gr, and then we have a function f of k added to this. And this makes us really manifest that what we have is just a modification of general relativity that effectively changes the k-squared part of the theory. Yet it does not introduce any additional degrees of freedom. So if one performs a very careful analysis, there are only 2 propagating tensor degrees of freedom in the theory. And in fact, it's known to be a particular subclass of such theories that can only minimally modify general relativity in this sense. Let me point out that there are other theories that are precisely of this form with an f of k correction to general relativity, such as the low energy limit of Horava-Lifshitz gravity, which is yet another proposal for quantum gravity, and this one explicitly breaks Lorentz invariance at a fundamental level. And the exact equivalence can be shown, the equivalence with the Quintin is manifest with a particular potential in that case. Let me say that other choices for f of k can in fact result in the same cosmological equations that one finds in other proposals for quantum gravity, such as loop quantum cosmology and also for group field theory. And those proposals have all something in common, and it's that their cosmological equations suggest that solutions are going to be non-singular bouncing universes. So all these ideas sort of merge toward the same same ideas. So let me wrap up. I started by saying that we might expect a theory of quantum gravity to exhibit some notion of limited curvature. And I asked the question, can we find a consistent low energy effective theory that could manifest this property? There's a neat setup, which is limiting extrinsic curvature, which allows us to construct such theories quite naturally. And they come up when you can select a preferred frame, such as in cosmology, by introducing this new field. I showed that a simple realization of this idea leads us to the Cos-Quintin theory, which connects itself with different proposals of quantum gravity. And this particular theory passes several sanity checks. It has stable linear perturbations, and it has interesting phenomenology, such as bouncing cosmology. There are further extensions that we can do and further phenomenology. For instance, we could add yet another curvature invariant to our action with another Lagrange multiplier to bound other curvature invariant functions, such as this combination of the contraction of the extrinsic curvature with itself and the trace of the extrinsic curvature. And the reason is that this quantity is equal to the shear anisotropies if we're in the Bianchi spacetime, rather than an FRW isotropic spacetime. And so we show that we can have solutions that are going to have not just bounded background Hubble scale, but also bounded shear anisotropies that way. And so in these theories, we have a very different approach to high curvatures. First, there's no singularities, and they're not going to behave in the usual mixed master Belinsky, Kalatnikov, Lifshitz type. Further directions, let me point out that we're working on trying to find specific observational predictions that such theories could have if they're present in the very early universe, that could allow us to show that these theories are falsifiable. And furthermore, we're thinking about exploring the stability at the non-perturbative level using techniques of numerical relativity. That's it. Thank you.
Okay, great. Thank you, Jerome. So questions?
Thanks for the talk. I have an extremely naive question. So at the beginning, you mentioned the need of a gravity theory